Hi, my name is Stephanie, and in this case, I'm going to talk about rotation in kinematics. Well, first, I explain the meaning of the rotation. Rotation in kinematics refers to the change in orientation of the robot. It's very simple concept, but it is important because if you need find a point or you need locate an angle, you must know how it is the interpretation, and it's very different when the meaning of the rotation is general, because the general concept is like movement that a figure performs and based on a fixed point. But in this case, if you need the orientation, because we refers to the robot or the machine. Then I want mention the extra rotatory system because it's the most common in the exercise of the books or another exercise. And the extra rotatory system um, consists in that when we locate a point or an angle in our Cartesian plan, the z-axis will always be positioned above, and the another axis, the x and y, at the sides. For example, in this figure, here is C because always is above, and at the sides we locate the x and y. Also exists rotation matrix, and rotation rotation matrix represents the rotation of the degrees of the plan and the direction. And for example, if you have three dimensions, rotation matrices represent rotations concise. And also it's important because if you have an example and with rotation matrix, you must know how is interpretation too. And identity matrix. Identity matrix or unit matrix is a square matrix where all its elements are zeros except the elements of the main diagonal, because these there are ones. For example, in this figure, here is the main diagonal because here locate the ones. For example, in x and y and z. Here is the first point. And finally, I have two examples. And the first example, it is a rotation in axis y. And for example, the rotation is when the axis in which the rotation is mentioned doesn't move. For example, in this case, is in y, and therefore that axis is not going to move, only the other two axes. Here we see where the final position. The position of the y, it's the same of the y1 because it doesn't move, and the rotation in x and psi for the two axes, the final result is here. And the second example, it's very similar except about the rotation, because in this case the rotation is in axis c, y in c. And for example, the axis of the rotation is x and y. Here is the final position for two y and x, but in C the position is the same because here is the rotation. And that's it. Thank you.
Yeah. So we have this example. In this one, we can see that it's a rotation in x. This is because if we see the rotational metrics that we saw in the past, we can see that it's pretty similar to the rotation in x. And first of all, we're gonna do the plane, the new plane that we have, and then we're gonna find this point in this new plane. So we can see that if it is rotation in x, it's gonna be x1 is gonna be the same. So this x1 is gonna be the same, the change. But we have that j and c is gonna to rotate 45 grades. So we're gonna have something like this. And this angle is 45 grades. 45 grades. This will respect J0 and C0. So this is J1 and C1. Now we're gonna find this point. We have the new orientation and we need to find this point. So we're gonna do something like this. 0, 0, 0, goes 45, minus 45, minus 45, goes 45. This is gonna multiply 0, minus 1, 0, minus 1. So we're gonna multiply this per this, and we're gonna sum this per this, and we're gonna sum this per this, and we're gonna do this with each file. Okay, so we have that minus 1 per 1 minus 1, 0 per 0, 0, 0, minus 1 per 0, 0. This is assume, and we have the result minus 1. Now, the next one. Minus 1 plus 0, 0, 0 cos of 45, 0, and minus 1 per sin of 45 is plus, because it's the same, plus sin of 45 grades, and this equals to sin of 45 grades. And the last one, 1 minus 1 plus 0, 0, 0 plus sin, 0, and minus 1 plus cos of 45, we have cos minus minus cos of 45, and we have the result cos of 45 minus cos of 45, and we have this is a matrix of 3 plus 3, and this one is 3 plus 1. So we're gonna have a matrix, another matrix, 3 plus 1. So we have the minus 1, the sin of 45, and cos minus cos of 45. And this is our new point. New point. If this is our new point, we only have to do this matrix with this point. Now we're gonna find this point in this plane. So we're gonna do this plane, something like this. This is x. We have this rotation, this y, and we have that we have to resolve this one. So we have something like minus 1, and we have that like this. We have sin of 45, 0.707, so we have 0.707. Now minus cos 45, we have minus 0.707. Now find this point. So we have something like 1, 2, 3. In J is in positive, so it's okay if we have something like that. But X is negative, so we have to trace the negative. And 1, 2, 3. So we have now in 0, we need negative 2. So we have to trace the negatives. It is 1, 2, 3. Minus 1, minus 2, minus 3. 1, 2, 3. Minus 1, minus 2, minus 3. So the first x. In x is minus 1, so we have the point right here. And is we are in x. Now we have to be in y. In x, point the x is this one. In y is 0.7. It's something like this. So we have to trace. We are in negative of x, so it's in this point, like something like this. And now we're gonna go to the 0.7 in this one, minus 0.7 in C. So we have something like this. This one, we're gonna change to right here, something like this. So this one is our new point in our rotation, and that's it. The orientation matrix has the application to let us find or describe how the orientation of a robot is, so we can know if the robot is rotating in X, Y, or Z. So we can only multiply the rotation matrix, for example, the rotation of theta, and we can only multiply for the new point, and with this we find the new orientation of the robot.
Now we'll talk about homogeneous transformation matrix. The homogeneous transformation matrix is represent the position and orientation of a rotate system and transfer it with respect to a big system. And transform a vector expressed in mobile coordinates and its representation in a fixed system, and rotate and translate a vector with respect to fixed system. This conforms a homogeneous transformation matrix. C is a matrix of 4 by 4 dimensions. They represent the transformation of a coordinate vector homogeneous from one system to another, and is composed of 4 terms: scaling, translation, rotation, and perspective. In the case of a robot with 2 grades of freedom, it's very easy to build the direct cinematics functions using a geometric proceeding. However, things get complicated when we extend the study to a robot with more degrees of freedom. Try to solve the problem using a geometric method. It's turned out to be very inappropriate. The the most appropriate thing is to use a reduced through linear algebra. For that, we are going to use the homogeneous transformation matrix. Um, we we are going to study translation matrix, and for this we are going to start by analyzing this small diagram. The first diagram, we are going to suppose that we have a system x0, y0, and z0. We are going to translate over this Cartesian system and quality A over the axis in in x, then quality B on the axis y, then quality C on the axis z. We here we are going to place our new Cartesian system we are going to try to find the relation that there is to make the conversion of coordinates from system 0 to system 1, assuming that we have a prefix point. Um, this prefix point can be expressed both in the system 0 coordinates with could be x 0, y 0, and z 0. Um, and P1 which would be x1, y1, and z1. Now, in this part, I will show you the translation result first. It will be given in the system 0 by coordinate x. However, in system x1 has coordinate x1, and we also have distance involucrate, and if we observe here the segment size x0 is given by the sum of a plus x1. That will be the first result. Now let's observe what happens on the axis y. We have a distance y0, which will be the distance marked from the origin of the zero system to the point P. We can also do this by adding the other two distance that will be B and y1. Then y0, I am left with the sum of b plus y1. In this case of z, the distance we travel to move the 0 system to system 1 on the axis z, where y the coordinate in the system 1 z1. I make this matrix products of the matrix 4 by 4 multiplied by vector of 4 by 1. Will in this case I will have x0 is equal to this one, which multiply x0, it will give me x1 plus a. In this case of y, we will have y1 plus b. In the case of z, we will have z1 plus z. This matrix that is formed for 4 by 4 is matrix that is now the relation matrix, while the three translation parameters that will be the three axes.
Hi, my name is Sebastián Monroy Valdez, and I'm going to explain you the example of homogeneous transformation matrix. Well, this is the example, and we have a translation in x and y. We have the value of y and the angle of the translation, and we can notate that the rotation is in c of 60 grades, 50 grades. Now, for the solution of this example, we use this reference system of 3D plane, X, C, and Y. First, we need to draw the rotation plane, and we remember that the rotation is in C. We put C in front of us, and the rotation plane is in X and Y. We draw the rotation plane and X and Y, X0 and G0, and we draw the 60 degrees, that is the rotation of this example, and we rotate 60 degrees like this. And now we draw the x1 and g1, and we can remember that x is equal to cos of 60, and and y is equal sinus the 60. Now we draw the translation plane, and we put equal to the rotation plane c in front of us, and we draw x and y. We draw x0 and y0. We put the 45 degrees that is in the example. The degrees of the is the grades of the translation. Now of the formula, we put x equal to L cos 45, y equal L sinus 45, and we put the L alone equal to 6 divided by sinus of 45, and we do this in our calculator, and we obtain that the value of L is equal to 8.48. Now we put the value of L in these equations like this: x is equal to 8.48 cos 40 cos of 45, and y equal to 8.48 sinus of 45. Now we obtain the value for x and y, and we obtain in our calculator that x is equal to 5.99, and y is equal to x, and we can say that this is equal to 6, and why c is equal to 0? Because we are rotating in c, and when we rotate in c, the value of c is 0 because c don't move. Now we for the graphic, we draw our 3D plane like this. We put c, x, and y. C, c0, x0, and y0. Now we draw the value of the x and y that we obtain in these values. We draw six, and in the six lines, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. And now here is our new point, and now here we draw our new plane, our new 3D plane, equal to this one: c0, x0, and g0. Now if I can tell you, before, c, it don't move because it we are rotating in c, thus it is don't move. C1 stay in c. Now we rotate G1 60 grades, and we draw the line like this, and it is rotating 60 grades, and x1 it is rotating 60 grades, and this is our graphic of this example. And now we do our homogeneous transformation matrix, like, we have the matrix of rotation of C here, that indicate us the cos of the angle, the sinus of the angle, and 0. Then in the second line we have minus sinus of the angle, cos of the angle 0, 0, and here in the third line we have 0, 0, and 1. And we put our homogeneous transformation matrix here. Cos of 60 degrees, sinus of 60 degrees, 0 and 0. Minus sinus of 60 degrees, cos of 60 degrees, 0, 0. We put 0, 0, 1, and 0. And now here we add a for line because we add the values the that the robot translation in the plane. We put that it move in x six space or six lines, and j in y it moves six lines too, and in z it moves zero lines because it is rotating in z, and we add one but because it indicates um, and now this is the complete explanation of the example. This is the solution. This is the complete solution of the example, like this. We have our rotation plane, the translation plane, value of L, the value of X, Y, and Z, and our graphic, our new graphic, and the matrix. And for final, I investigate that an application of the homogeneous transformation matrix is that we can apply this matrix in the control of cinematic positions of an articulate robot of 3 degrees of freedom. And this is an image of the example of an articulate robot of 3 degrees freedom. And thank you for your attention. This is all of the example and the application of homogeneous transformation matrix.